Okay. So if you recall, yesterday we obtained the canonical Hartree-Fock equations in the spatial orbital basis. So today, so yesterday we started with the spin orbital canonical Hartree-Fock equation, and we obtained the analogous spatial Hartree-Fock equation. So this is the spatial one. And now we need to get this into a form which is numerically solvable. So the first thing we must do is convert this equation, which is in operator form, into some sort of matrix equation which can be solved through methods, through algebraic methods as they are called. If you just look at this and you remember that the Fock operator contains the kinetic energy operator and the nuclear attraction and the Coulomb repulsion, then it would appear that this is a differential equation, right? But we don't want to solve it like this. It is much simpler to solve a matrix equation. So that is what we will try to do. So the first thing we need to do is we want to express the size in terms of some known functions. Let's say we have a set of known functions, phi mu. Then these are a set of known functions which is called a basis set. Now what this basis set should be for molecular computations and how we will choose them, we will talk about that in quite some detail in a later class probably. Okay. For now, let's just assume that we have a set of known functions, and I write the spatial part of my molecular orbital, which are the solutions to the Hartree-Fock equation, as a linear combination of these functions. Okay, so the phi mu's are known and the c mu i's are unknown. So once I have a basis set, an unknown function, the problem of determining an unknown function is reduced to the problem of obtaining the coefficients, the set of coefficients c mu I. And here we have a set of k. So the phi mu. So we have k phi mu's, which is flexible. The number of molecular orbitals, the number of occupied ones is fixed at n. So as long as my basis set contains more than n functions, I can represent all the occupied orbitals. So in principle, if k is infinite, then I can represent any psi I. Then and then phi mu, the set phi mu is called a complete set. And as you know, with a complete set of basis functions, you can represent any function. However, in practice, you can never have an infinite set. So you will always have a finite set, let's say with k, and then the accuracy of my psi I will be determined by this value. So when you say that you have this Hartree-Fock solution, what you normally mean is that you have the Hartree-Fock solution in a given basis. And if you increase the basis size, you will get a more accurate Hartree-Fock solution. So sometimes people distinguish between the Hartree-Fock solution and the Hartree-Fock approximate solution in a given basis. But these two terms are not rigidly used, they're interchangeably used, and in all practical cases, you have a basis set. Okay. You can do computations in basis sets of various sizes and extrapolate it to the infinite limit, and then you would get the best possible Hartree-Fock solution that you can get. Okay. So this is, and just so that you have some idea, the phi mu's are normally the atomic orbitals, and the psi i's are the molecular orbitals. So that is the best guess or the most intuitive way of doing molecular computations. In principle, they could have been anything. They could have been a set of Gaussian functions, they could have been polynomials, they could have been anything. But the most practical way of thinking about molecular computations is that the basis functions are the atomic orbitals and the solutions are the molecular orbitals. And from this relation, it is clear that every molecular orbital is then a linear combination of atomic orbitals. And you have come across this in a less mathematical context when you have learned the molecular orbital theory, and this is called LCAO. So the linear combination of atomic orbitals. So mathematically, it is basically the way of solving the Hartree-Fock equations. So let's move on. We can put in this expansion now into the canonical Hartree-Fock equation, and we get FR1. Don't mind me missing the hats or putting them sometimes. This is sum over mu to k c mu I phi mu, and this is equal to epsilon I. I can write II or I, whatever you like. Sum over mu c nu I phi nu. Okay. And then I can multiply by phi by another phi star. Let's say okay, let me put both these in the same with the same sum. It's the same thing, no problem. Then I can use phi mu over here. And I integrate over dr1. So let me do that. Then I get integration phi mu star r1 f r1 phi nu, that is also r1, sum nu c nu I is equal to epsilon I dr1. Okay. And this I now define. Sorry, I should put this here. So sum nu. So this is a matrix element of the Fock operator. Don't need to write this when I use Dirac notation. So phi mu nu c nu I is equal to epsilon I sum mu c nu I. And here we will write the overlap of the two functions as S mu nu. So so in the previous classes, we have been quick to assume orthonormality of spin orbitals, of the spatial part of the spin orbital, and maybe in some other things also. We've just gone ahead and assumed orthonormality. But here you will see that this overlap S mu nu will play a very problematic role, because the atomic orbitals that you choose, they so you have various atoms in a molecule, and you want the basis sets to be atom specific. So it is not possible to ensure that the atoms that some function of one atom and another function of another atom, they are orthogonal. So then what would happen is the atomic orbital basis would become specific for a molecule. And you can imagine that this, since there are like almost infinite number of possible molecules, this would be a very, very inconvenient system. So it's much better to have atom-specific basis sets and not assume their orthonormality and keep their overlap. Okay. So that is why in the case of this atomic orbital basis, the orthonormality is not assumed when we're deriving things. Okay. But it will also create problems, as you will soon see. So here we write this as the overlap S mu nu. Then, and this you can write as some sort of matrix element of the Fock operator in this atomic orbital basis. Okay. So I can simplify this more with this notation. So F mu nu C nu I is equal to epsilon I sum nu S mu nu C nu I. So immediately you see this is a matrix equation. So in terms of matrices, I can write this simply as Fc equal to Sc E epsilon. And this is what is called the Rutan equation. So the idea of representing the solutions in a basis and then converting it to a matrix equation, this was done by Rutan, and hence this is called the Rutan equation. So let's now think of what this equation contains. It contains some sort of matrix elements of the Fock operator in spatial representation. It contains some matrices C, which tell me what linear combinations of the atomic orbitals we must take to form all the molecular orbitals that we want. S is the overlap of the atomic orbitals, and epsilon is the orbital energies. So it is illuminating to look at the dimensions. So this is the Fock matrix in atomic orbital basis. So let me call it NaO. So it is NaO by NaO. The coefficient matrix, remember, it was defined as a combination of the atomic orbitals to give me the MO. So it is NaO by NMO. Does this work? Okay, this is this. S is NaO by NaO. C is again the same, and epsilon is NMO by NMO. So dimensionally, everything matches in this matrix equation. So that looks like a nice and clean equation, but how will we solve it? This is not an eigenvalue equation. Right? But before we do that, we also need to know how to evaluate the Fock matrix elements. So what is F mu nu? So remember that my Fock operator Okay, I haven't written it, so let's write it again. So the fork operator, so we will do the fork operator. Now we will talk about that. So what is F mu nu? So the fork operator in spatial orbital basis, that was the one electron part plus a sum over all the spatial orbitals. So capital N is the number of electrons, and you had two times the Coulomb operator minus 1 times the exchange operator. So why? So last class we saw why we have this factor 2, which is absent in the spin orbital expression. Then if you look at the mu nu integral now, so what is F mu nu? It is an integral of 5 star mu 1 F1 phi nu 1 dr1, right? The one electron part, that gives me what is called the core Hamiltonian. So now I'm introducing some more terminology. So the one electron integrals are called core integrals. So you have a so, and the two electron part needs to be evaluated. So what does that look like? So that is A equal to 1 to n by 2 integration phi mu star 1 so what is the problem here? Why am I going through all this trouble? Because A is a molecular orbital. And I don't want a mixed integral of atomic and molecular orbitals. That is not neat at all. Okay, so you want either atomic orbital integrals or you want molecular orbital integrals. So now I'm trying to go over to one of them and not have a mixed integral. So phi mu star 1, and then you have the Coulomb integral, which looks like, so let me write dr1 here. So now this is mu nu. So mu a nu a, okay, 2 of that minus mu a nu 1 of that, then phi nu 1 dr. So is this clear? So I've just written out the operator, the Coulomb and exchange operators in terms of integrals, and I have my phi mu and phi nu. Okay. And now what I do is I write the MOs involved here, that is A, in terms of AOs. So this is there. And now I'll have a sum over the AOs. Let's say I have a lambda. So 2. I don't have enough space to write it. Sorry, 1 second. Let me erase this. That's why a blackboard is better than an iPad. You have more space to write. So it is this plus sum A equal to 1 to n by 2. So if I just write the expansions, I hope you will be able to do it. So here you have the starred ones. So here psi A is starred. So when I expand that, I will get a C star sum over, let's say, lambda. So C nu A from here. And from here, I will get a C, let's say, summed over sigma C sigma A. Okay. And the same from here. Here, from the exchange integral, you have a starred one coming from here and an unstarred C coming from here. So you will get the same thing. So I can take that common and write 2 now mu lambda uh, no, sorry, mu nu sigma. So the sigma is the unstarred one, nu sigma minus mu mu lambda sigma nu. Okay. So this is the expanded one. And of course, we still have the integration on mu nu. So that is still there. And I again have no place to write it. So I've not written the coordinates. I hope that's okay. So then you continue with the core part. Plus. So what are we doing here? What did I do wrong here? So I made a very big mistake here. Have you all seen that? No? So when I have formed the integral, the Coulomb integral, and I've put the nu inside here, over here, then obviously I have done the integration on phi mu star. That, so there is no need to have the phi mu star over here anymore. So what did the Coulomb operators contain? The Coulomb operators were integrals of R1 to inverse and what? So who remembers the form of the Coulomb integral? No? So what does J operator look like? Okay, so let's go back and look at the expression that we did. So here you are. So now what did it look like? So it was an integral of only one spatial orbital over here. So you see, this is the Coulomb operator. And then when you take the expectation value of the Coulomb operator with respect to any, you get sorry, which is this one, which I have written over here. So obviously, I should not have continued with writing the integration over phi mu star. Is that clear? Is it clear what a mistake I made? No? So here I have already taken the expectation value of the Coulomb operator with respect to mu and nu, and that has given me the Coulomb integral. So that simplifies a lot what we want to do. Oh, and how did this get erased? This is lambda a. Anyway, so then this integration is gone. So none of this should have been there. I have already taken the expectation value. So I get this and this. And now I will define something new. So I will sum the coefficient matrices over A, which is the MO index, the molecular orbital index, and call it a density matrix P lambda sigma. So this is called so P lambda sigma is called the atomic AO density matrix, or atomic orbital density matrix. So F mu nu depends on the atomic orbitals, and it depends upon P, where P is the let me just write it in matrix notation. So F depends on P. These are the matrices. So what have we done? So we had a Fock operator which depended on the molecular orbitals. And when the Fock operator depends on the molecular orbitals, what it means is that it depends on the coefficients of the basis set C. And when we take the matrix of this Fock operator, then the matrix can be reduced to something that depends on a different quantity, which is formed from C, of course. It is equivalent. And we say that the Fock matrix depends on the density, atomic orbital density matrix. To compute which, you need to know C. So why do we go from C to P? That is because of the numerics. So you see, C has a much larger dimension. It is NaO by NMO, and every time you construct the Fock operator, you would have to do a matrix multiplication of C star and C. But the density matrix, it is only NaO, or number of atomic orbitals by number of atomic orbitals. So that is normally much smaller, and you can store it. Okay, so that is why. So from the point of view of storage, it is beneficial to go over to the density matrix. And that is why we define this quantity. Anyway, so this was sort of a side note just to understand what F mu nu is. We will now go back to solving the Rutan equation. So do that to solve. So how will we solve? How to solve FC equal to SC epsilon? So let's see. So if we did not have S, it would be an eigenvalue equation. And we would simply diagonalize the Fock matrix. But now, because of this S, we cannot do this. So what is the best way of removing this S? Can anyone suggest what we can do? So what we can do is we can go over to a different basis that will give me a C prime that will give me an eigenvalue equation as the Rutan equation. So let's put that into mathematical terms. So we have now a basis or a transformed basis that looks like this. So what have we done? We have said that I have gone from phi mu to a set phi mu prime such that my coefficients are related by this relation, which means that my original C is xc. My original C is xc prime. So now if I was to put xc prime into my Rutan equation, what would I get? I would get fxc prime is equal to sxc prime epsilon, right? So does that help me in removing s in any way? With a some choice of x, can I remove s? Yes or no? Anyone?
Are we diagonalizing?
Mm, no, we're diagonalizing what?
I mean,
I'm just
the
asking.
x.
I'm asking. Can you get some s which will remove the s from my equation? Do you think you can remove it?
Don't know. Basically, x equals to s inverse. I don't know if we can choose it or not.
Uh, you can. Okay, you can remove it from the right, but then the s would reappear on the left if you just choose x equal to s inverse. That is not a. That will not solve my problem. Anything else we can do?
If you choose
Okay,
unitary
let's.
matrix for x, then it transforms. Oh, no, no, it is not correct. Sorry.
So you're not very far actually. So okay, let's do one more step. So what is done is you multiply with x dagger. Okay. Okay. So now can you choose a x that will remove the s from the right?
Yes, this is basically the eigenvectors of S that will transform it at the unitary matrices for the right side.
Yes, very close. So there are two options. So one option is you take x equal to s to the power minus half. And the other option is you take x as some unitary matrix multiplied by s to the by the eigenvalues, square roots of the eigenvalues of s. So small s is eigenvalues of capital S. So, but we will do that in a little more detail now. So don't. So you will see what is happening. So let us see. 1 minute. Okay. So consider this. So what we want basically is that this phi mu prime is an orthonormal basis. Then my S prime would basically be the diagonalized S. Then it would, if it's just the diagonalized S, it would still not be orthonormal. It would only be orthogonal. Why? Because U dagger SU is basically small s, which is the eigenvalues. It's not unit matrix. But what we want is x dagger Sx to be a unit matrix. So this is the difference. So simply choosing x to be the diagonalizing matrix is not enough. You want the set to be orthonormal. So then what you have to do is you have to uh, divide by s, and if you want to just change u, you divide by the square root of s. So x can be taken to be u s to the power minus half. That is one choice. Then this would become a unit matrix. Right? So this is what is called canonical orthogonalization. So this choice is called canonical orthogonalization, which is in effect orthonormalization. Okay. And the more, so this is actually the smart way of doing things. There is one more method which is called simply symmetric orthogonalization, and that is you have FC equal to SCE, and you have taken F. It was C prime is, so C is X C prime, so X C prime equal to S X C prime epsilon. and x dagger fx c prime. So these steps are the same. And x is equal to simply the whole matrix, square root of the whole matrix. So then you would get x dagger fx c prime equal to s to the power minus half s to the power minus half c prime epsilon. That would become a unit matrix. But okay, so we have converted this into an eigenvalue equation, but it is no longer the eigenvalue equation of f. It is the eigenvalue equation of x staggered fx in both cases. So the final form is the same in both cases, whatever you choose for x, and that. So now we have an f prime then, c prime equal to c prime epsilon. This is an eigenvalue equation for f prime. So does that help me in any way? So earlier we did not have an eigenvalue equation, but we had the original Fock matrix. Now we have a transformed Fock matrix, but we have an eigenvalue equation. So this latter situation is now actually much more beneficial, because if you had Fc equal to SCE, we didn't know how to solve it. Because we have unknowns, we have the coefficients as unknowns, and we have epsilon as an unknown. And the only matrix method we know to solve for two unknown matrices, I'm being very rough here, so is the diagonalization method. And in order to be able to solve an equation by diagonalization, you need eigenvalues. So our trade-off is beneficial for us. So now we have to transform our Fock matrix with the with some components of the overlap matrix, but we have an eigenvalue equation which we can directly solve by diagonalization. So this is a solvable form of the equation. Okay. Now the other important thing to note here is that f, or equivalently f prime, depends on C, or you can say it depends on the density matrix as we defined it. So once I obtain C prime, it is not a one-step process. I have to recompute F prime and diagonalize again. So that is why the Hartree-Fock equation, or the Rutan equation, is not simply an eigenvalue equation. It is a self-consistent field equation. So what is happening? So I have to take a guess for C or P. I will tell you exactly how it is done afterwards. So now I'm just trying to show the path that you have to either guess C or P. Then you construct your F prime. So these are just the rough steps. Okay, I will give you the algorithm in just two more minutes. So you have to guess either C or P. You have to construct F prime, diagonalize it, obtain epsilon, obtain C prime. Then go back, recompute F prime with the new C's, and repeat this till your C's or C primes no longer change significantly. So you decide a threshold at which you want your equations to converge, as it is called, and when it converges to that level of accuracy, you stop. So then solve eigenvalue equation, recompute F and F prime, solve eigenvalue equation. Okay, so this is the same and loop. Okay, so that is how you solve it. So if I want to put it in now greater detail, so let's say I'm going into the finer details. So the very first thing that you need to do is you need to specify your molecule in terms of a set of nuclear coordinates. So specify molecular, so that is what is called the molecular geometry. So let's say if it is water, then I need to specify the bond length, the bond angle. Okay, so R alpha. And if you do it like this in terms of bond lengths and bond angles, it is called the Z matrix representation. You can also specify the Cartesian coordinates for every atom involved. And then this is called the Cartesian representation of the geometry. Okay. So this is the first step. Then you have along with this, so in the first step you need the geometry and you need to decide on the basis set that you will use for each atom. So these have various names. So they are called things like STO G, STO3G. Then you have CCPVDZ. So correlation, consistence, polarization, balance, double zeta. We will talk about what these names mean in a different class. So there will be some names, and you can specify either the same basis set for each atom or different. Now these have specifications depending on the atom. So you have an STO 3G basis set for hydrogen, you have one for helium, one for lithium, etc., etc. And again you have CCPB-DZ level basis set for hydrogen atoms, hydrogen, sodium, fluorine, all various atoms. And these are present either inside the package that you are using or in a database online. So then you have to select the basis set. And in choosing your basis set, you have to consider what you want, what sort of property you want to calculate, etc., etc. So this comes with experience. And once you have the geometry and the basis set, you need to compute the atomic orbital integrals. So notice that in the final equation that we decided to solve, we no longer have molecular orbitals. They are all atomic orbital integrals. So where is it? Oh, so here. Okay. So here you have the atomic orbital integral of the core part of the Hamiltonian, which is the kinetic energy and the nuclear electron attraction. And you have the Coulomb and exchange integrals of the atomic orbitals. So and the atomic orbitals are part of the basis and it does not change during the computation. So you only need to do that once and keep it. So compute the atomic orbital integrals. How will you do it? This is done numerically. And we will also talk about how this is done in a different class. So we will have one class where we go through the details of all these technicalities. You compute them numerically and keep them. Okay. So for the kinetic energy integrals, you'll have to, so the operator is a differential operator. So you'll have to differentiate the basis function that you have taken. Okay. So you need to have ways of doing this. And once you have the integrals, uh, you can compute the Fock matrix. Of course, you can compute Fock nu, F mu nu. You also have, so you can compute it. But remember, F mu nu also contains the MO coefficients or the density matrix. So just knowing the basis or the atomic orbitals is not enough. This requires P mu nu. So where will we get this P mu nu from? P mu nu needs my MO coefficients, which are actually the answer to my equation. So you start with a guess. So you need to guess P mu nu, okay, before you compute F mu nu. Fine. Then you get the full F mu nu. There is the 1 electron and the 2 electron and everything, all the contents. Then you also have the overlap matrix computation. Then you diagonalize it. Okay. And you obtain X. That is, you might and when I encounter linear dependence, diagonalizing my overlap matrix will give me near zero eigenvalues. So that is not good, because this will then create problems when I diagonalize my transformed Fock matrix as well.
Madam,
So you
could you
eliminate
repeat
it
it?
at
You was little inaudible in the last few seconds.
ah okay, I can repeat it.
After
So
SMU computation,
in order to, yeah, okay, so S mu nu computation, and then we will diagonalize it to get this transformation matrix X. Okay, but we can encounter a problem here, which is that my eigenvalues can become close to zero. And remember, we have to multiply my coefficients then with u dagger s to the power minus half, will then blow up to infinity if my small s is very small. And what does it mean to have very small eigenvalues? The atomic basis that I have taken has linear dependence in it. And why is this possible? That is because the basis sets that we take comes from a data set which is for every atom. And like I was saying, you can take various combinations of various basis sets and different atoms and different molecules. So you don't know a priori that all the basis functions that you have in your set are linearly independent. So this is a common occurrence that when you try to diagonalize S mu nu, you have very small eigenvalues. So to eliminate this, you need to decide a threshold to throw away these small eigenvalues and the corresponding eigenvectors. And once you do that, your coefficient matrix, so C, which has the dimension of atomic orbital and MO orbital, this then is no longer a square matrix. So this is NaO, this is no, sorry, okay, no, you cannot reach this conclusion just yet. I need to tell you one more thing. Okay, I will not talk about this now. So you throw away the small eigenvalue. So what happens is that from your set phi nu, it is already reduced to, so it will be reduced. Let's say it will be effectively reduced to some phi prime mu, which is smaller set. Okay, but this is only implicit. So you will only throw away the eigenvalues, and then your X will become a rectangular matrix. X is you dagger x to the power minus half. X is rectangular. Yes. So X will become rectangular. Yes, that is it. So you have to take care of that. Then once you get X, you can compute your Fock matrix, transform your Fock matrix. Then you can do this. Then you solve the eigenvalue equation. F prime C equal to F prime C prime. Okay. So you obtain C prime. Then you go from C prime to C. How do you do that? C prime is equal to X. Sorry. So you get C prime, and then C is equal to X C prime. Fine. Then you get the new P mu nu, and then you check convergence, which means you check the energy you obtained from the previous step against the energy you obtained from the current step, and see if the difference is too small, is negligible, or too small, smaller than the threshold that you have set for accuracy. So that is called checking for convergence. And if it has converged, you stop. If it has not, then you go back to computing F with mu P. Okay. So there are lots of little things involved in every step. The basic procedure is, as I said before, that you have to simply obtain C prime, construct F prime, and obtain a new C prime. So that is the basic procedure. But when you want to do an actual computation, there are little details involved which you have to take care of. So I am over time. I am sorry. I hope I am not encroaching on some other class. So I will stop here today. And on Monday, the first class will be taken by Vivek, our TA, because some of you wanted to have a LaTeX tutorial, so a LaTeX tutorial. So those of you who know LaTeX can opt out. I will take the class again from 10 o'clock. From 10 to 11, I will take it. So from 9 to 10, Vivek will give a LaTeX tutorial. Okay. I will write this on WhatsApp also, because I think some of you might have left already. So thank you for today's class. Please stop the recording. Thank you.